Hello, hello everyone. Um, Today we are continuing with the density of state derivation. In the previous class, we have discussed density of states using the quantum mechanical treatment with the help of Schrodinger wave equation. Using the Schrodinger wave equation, we finally arrive an expression for the eigen energy values or energy quantization. Using the energy quantization, so that is En, which is equal to n square h square 8 ma square, so which is equal to h cross square k square 2m. So this is an kinetic energy of an electron, and we are representing this energy eigen energy states in nx square in k space. For example, nx square plus ny square plus nz square divided by 8m a square into h square. So here nx square plus ny square and nz square are a positive real numbers, so that is the quantum states. So using this expression, we have construct the Fermi sphere, and we obtained the density of state expression, that is n of e into dE, which is equal to f of e into dE, f of e z of e into dE. So then we got the final expression, that is the substitution of all these the probability deciding factor as well as the number of available energy states in the energy range e to e plus dE. So we obtained an expression n of e dE, which is equal to pi by 2 8 m divided by h square 3 by 2 the volume and e power of, and the Fermi factor 1 over 1 plus exponential of e minus ef by kBt into dE. So this is the expression which is having the product of both the Fermi factor as well as the density of available energy states. So here, so we have to check now, so what is the variation of n of e into dE as a function of the Fermi energy. So that is the distribution is as shown in figure. So now we are going to plot variation of n of e divided versus the Fermi energy, or in terms of energy. In general we will say or you can say n of e versus e energy. So because there is a straightforward relation, n of e into dE is directly proportional to e power of. So in terms of energy we are going to plot. So the distribution is as shown in figure. So this is so here this is an n of e, here this is energy, and the curve is like that. So it is showing some parabolic. At some point it dropped to Fermi level. See, up to here in this area. So that is energy of the occupied state, nothing but the valence state. So here all energies are filled according to the Pauli exclusion principle. So now, according to Pauli exclusion principle, so the same diagram I am representing here like this. So for example, these are the valence band. According to Pauli exclusion principle, not more than 2 electrons can occupy the same quantum state like this. So up to here it is a Fermi level. So now here, so whatever the dropping point, up to here this is the dropping point. So this is leads to up to Fermi energy, mean all these states are occupied. So means the valence states are occupied in this region. But up to here these are the valence state, and these are the above this EF, these are the available states. So here you can see the expression here. So this is the Fermi factor. Of course the Fermi factor is a probability deciding factor with respect to temperature. So for example, you see that is 1 over 1 plus exponential of E minus EF by kBT. Based on the condition whether E less than EF at T is equal to 0, whether E greater than EF at T is equal to 0, or E which is equal to EF at T greater than 0 Kelvin. Based on that, you can decide the probability of occupation electrons in the available energy states. So for example, in this diagram, so all these are the filled state. Above these states are vacant, nothing but the available energy states. The same way, at this point, these are all the filled state. So over here, above the CF, these are the available states. So because in metals, the valence band is completely filled up to the Fermi energy. So now, if you rise the temperature, usually in the graph we know that it is a parabolic curve. Up to here it is a parabolic, and here it will be very like this. So this is the case when the temperature is greater than 0. I consider here if energy is less than EF at temperature T is equal to 0 Kelvin. So then the probability of finding the particle is F of E is equal to definitely 1. We will show you the probability factor F of E is equal to 1 in the later section. So what happened? At temperature T is equal to 0, T is equal to 0 Kelvin. See, according to Fermi energy definition, at absolute 0 Kelvin, all the valence bands are completely filled. When temperature is greater than 0 Kelvin, so the electrons are occupying the higher energy level. So now, this state, whatever the dropping point here, this is called the Fermi level. This one is the Fermi level. The corresponding energy is known as Fermi energy. Okay. Then, if temperature is greater than 0 Kelvin, what happened? The curve is slightly changes like this. So now if the temperature is raised greater than 0 Kelvin, then the valence electrons, they are occupying the higher energy level. See that these electrons are start occupying these available states like that. You have an Avogadro number of atoms in the solid. For example, you can consider the copper. The density of atoms is 24 of 28 per meter cube. So let's individual atom or contributing electron for the participation of electrical conduction. So that as the temperature is raised, if T greater than 0 Kelvin, so then the electrons are start occupying the higher energy level. See here, this is the it is greater than so these electrons are start occupying the higher energy level. The graph is showing here not up to the Fermi level, so above the Fermi level, So this curve is temperature is greater than 0 Kelvin. Similarly, if you increase the temperature furthermore, you can increase the temperature furthermore. So of course you will get the curve up to here. Like this. So it is temperature is very much greater than 0 Kelvin. So now based on that we have to find out this N of E. So means here the electrons are start occupying the higher energy level. So here the product of both the Fermi factor F of E as well as the available state Z of E. The product of these two, F of E and Z of E, which gives the density of states N of E, this N of E. So we will see next. Next step. So the general expression for already we have written N of E, which is equal to pi N of E into dE, which is equal to pi by 2 8m by h square 3 by 2. So V into e power of into F of E. F of E nothing but you have 1 over 1 plus exponential of E minus EF by kBt into dE. So now we know that at temperature T is equal to 0 Kelvin and the condition energy is very much less than EF, nothing but you just observe here the Fermi energy is more and energy is less. So then the Fermi factor F of E is equal to 1. For example, make a clarification here why it will happens. Consider the Fermi Dirac distribution function, that is the Fermi factor. So apply this condition to this Fermi factor. So that is 1 over 1 plus exponential of E minus EF. For example, here the energy is very much less than the Fermi energy, so that you have an exponential. So E is less than EF, so that neglect this E, then exponential of EF by kb of 0 because temperature is 0. So this will be 1 over 1 plus exponential of minus EF by kb of 0. The entire quantity is minus anything value divided by 0 is infinity. So exponential of it is minus infinity. Exponential of minus infinity. So which is equal to 1 over 1 plus exponential of infinity minus infinity is minus infinity itself. Okay. So then this minus infinity is very less than this one. Of course it is minus infinity. One is a valid thing. Minus infinity is very uh, small quantity, so that you can ignore this minus quantity. So then this leads to 1 over 1, which is equal to 1. So this is the probability deciding factor f of e is equal to 1. So earlier we shown f of e is equal to 1 when the condition is e is less than ef. So of course you got f of e is equal to 1. We got the Fermi factor f of e is equal to 1. So then start substituting this f of e over this expression. So then the n of e into dE, which is equal to pi by 2 8m h square 3 by 2. You have a volume as well as e power half. So but the entire Fermi factor, so this Fermi factor f of e is 1 because the probability is 1. So of course here it is 1. Simply the expression, the above expression becomes pi by 2 into a pi 8m divided by h square 3 by 2 v into e power half into dE. So then we got this expression. So now we have to integrate this n of e into dE from 0 to up to Fermi level. So now this integrate n of e into dE, which is equal to, take the constant outside the integral, pi by 2 8m by h square 3 by 2, and integrate this from 0 to Fermi level ef e power of into dE. So of course all these are the constant quantity. Integration of n of e, it is both dE and integration both are going to be cancelled. You simply get n. It is a function of e. Of course I write here it is simply n. So which is equal to pi by 2, then 8 m. So whatever I written here, this volume element I considered, so this v is equal to a cube. Earlier we used to say this is the lattice parameter, the volume element. So I written as it is, for example here it is a square divided by h square, so 3 by 2, and the integration of this, of course you'll get e power 1 plus 1 into 1 divided by half plus 1. If you do the integration, you'll get this. So you have to apply the limits e to ef. Then this becomes n, which is equal to pi by 2 8m a square divided by h square. So it is e power, if you apply the limits, it is ef 3 by 2. So 2 plus 1 3 divided by 2. So this here it is 3 by 2. So again further you can write down one more step, n is which is equal to pi by 2 8m a square, sorry I forgot to mention here 3 by 2 divided by h square 3 by 2, and it is simply e f 3 by 2 into, it goes to the numerator, it is 2 by 3. Now, so here n, which is equal to, you have here a denominator 3, 3 into 2, 6, and you have here 2, so 2 ones are 2 threes are, it is simply pi by 6. 8m a square, sorry, it is 3 2s are 6, 2 ones are 2 threes are, it is pi by 3, pi by 3. 3 by 2 EF power 3 by 2. Now, so this is, we got it's n of E is n of E, so that is the density of states, density of occupied states. So this is it is a understood, it is n of E, here also it is n of E, here also it is n of E, it is a function of E. So now this is an expression of n of E, that is a density of occupied states, means the electrons are occupied available energy states, and the probability factor is deciding, so what is the probability. Now we will check, so that, so therefore the number of electrons per unit volume of electron is the number of, therefore the number of electrons per unit volume, number of electrons per unit volume is given by so we want to calculate the density of electrons, of course. So that is the number of electrons per unit volume of the system. So that is, whatever the electrons are occupied, the higher energy level, we have to calculate the density. So means the n, this is the density of electrons, n, which is equal to the number of occupied states, n of E, divided by total volume of the system, V. So which is equal to, we know that this n of E we already written, so here this is pi by 3, and here you carefully observe, here this is a power 2, denominator you have 2, 2 gets cancelled, it is a cube. So of course this a cube is nothing but volume element. So simply 8m divided by h square 3 by 2, and you have here the volume element, and volume element e power 3 by 2, that is EF towards per unit volume, because here n of E divided by V, but here this is the volume element divided by V. So let's V gets cancelled. Then, so this equation takes the form, so for the next step, so we got n, which is equal to n of E divided by V, which is equal to pi by 3 8m by h square 3 by 2 EF 3 by 2. So then I want to calculate this Fermi energy. EF, because the Fermi energy is the maximum. This Fermi energy is the uh, level the, the conduction process start taking place in solids. So EF power 3 by 2. So just cross multiply this. It is 3n divided by pi. I took this EF power 3 by 2 in the left hand side, and this is cross multiply 3n divided by pi and divided by 8m divided by h square whole power 3 by 2. Then I simply make an arrangement. So EF, which is equal to 3n by pi. I just send this denominator to numerator. It is simply h square divided by 8m three by 2. Next, I want EF. So here, if you do such, so up to here it is 3 by 2. I want Fermi energy EF. So it is h square divided by 8m, because this 3 by 2 goes to here. So then you will get the power is 1. So here this power is 1, and 3n divided by pi whole power 2 by 3. Then see, all these are here a constant parameter. So h square by 8m 3 pi, all these are the constant quantity. So then EF, which is equal to, if you substitute all these parameters, so that is a Planck's constant 6.626 into 10 power minus 34 whole square divided by 8 into the mass of electron 9.1 into 10 power minus 31. So 3 divided by n, sorry, it is pi, not n, into n power 2 by 3. So if you do the calculation, all the calculation, you will get the constant quantity. So that is 0.58 into 10 power minus 37 n power 2 by 3 joules. So if you do the calculation of all these things, you will get 0.58 into 10 power minus 37, a constant quantity. It is in terms of joules. So convert this into electron volt. You'll get EF, nothing but you have to divide it by 1.6 into 10 power minus 19. Then this will becomes 3.65 into 10 power minus 19 n power 2 by 3. So it is in terms of electron volt. So this is the Fermi energy. So here this expression is a Fermi energy, and it is very useful quantity, because whenever we use the free electron model, which is quite often, the value of EF gives the topmost energy level at absolute zero. So hope you are getting the point. So once again I repeat. So this EF is the expression for Fermi energy, and it is very useful because we can use this in case of free electron model, because in free electron model we know that according to the Drude model, so electrons are completely free they are moving throughout the solid. So you can consider the throughout solid, the potential energy is constant, that is V is equal to 0. So in case of free electron model, the value of Fermi energy, which gives the topmost energy level at absolute zero. I mean that we shown in the previous case, at t is equal to 0, the energy is very much less than EF. Means it gives at absolute 0 Kelvin, it gives the topmost energy, nothing but the Fermi energy. So the Fermi energy, uh, so for different materials, you will have a different Fermi energies. For example, in the most of the cases in the laboratory, we are doing the Fermi energy of determination of Fermi energy of copper. So, so we used to get around 6.7 to 7 electron volt Fermi energy. So for copper materials. So in a single derivation here, we have calculated the energy quantization using the Schrodinger wave equation. So the summary of the topic. So we arrive an expression for energy quantization, that is En is equal to n square h square divided by 8 ml square using the Schrodinger wave equation. So based on this expression, we derived the density of states expression. We derived Z of E into dE, which is equal to pi by 2 8m divided by h square 3 by 2 in the volume element and e power of into dE. So this is the number of available energy state in the energy range E to E plus dE. So later we arrive an expression for n of E into dE. It's both the combination of Z of E, nothing but this expression pi by 2 8m h square 3 by 2 and the volume element V e power of into dE, as well as the Fermi factor expression 1 over 1 plus exponential of E minus Ef by kVt into dE. So after this expression, so we arrive an density of electrons that is equal to around the density of electrons pi by 3 8m divided by h square 3 by 2 EF 3 by 2, sorry, EF 3 by 2. So finally we have calculated the Fermi energy EF. So that is 3.65 into 10 power minus 19 n power 2 by 3 electron volt. So all these parameters we have evaluated. One is the eigen energy values, that is the density of available energy states and the density of occupied states, and also density of electrons occupied in higher energy levels, as well as the Fermi energy of the solid. So this is the summary of the entire derivation. So based on this, we can calculate the transport properties of solids. Uh, so here I'm completed the concept density of states and its physical significance. Thank you.